Move on to Chapter 3, Network Protocols and Communications. We're going to talk about the rules of communications on networks, how we ensure that data gets to the place it was intended to get, and how it gets there in the right way so it can be translated, and data transfer within a network. So first off, there's some rules of communication on networks that we need to be aware of. Networks come in all shapes and sizes, but the device on the network has to understand how to communicate with all the other devices on the network. So they have to have these protocols in place for that purpose. So the communication begins with a message that is sent from a source to a destination. And the Cisco Academy uses the analogy of human communication, people talking back and forth to each other to demonstrate this. So they send a message, whether face-to-face or over a network. We have certain protocols in place. So a protocol is a set of rules. It's a fancy word that just means a predefined set of rules. If I want to send a letter in the mail, there's a protocol, right? I have to put it in an envelope of some sort. I have to put the destination address. I have to put my address. I have to put a stamp on it, right? I have to seal the envelope. That's the protocol that's in place to physically snail mail something, if you've ever done that. Some of you are young enough, maybe you have not. But that's the protocol for mailing a letter. And in the same way, we have protocols in place. So if these two computers have not established a protocol for their communication, they cannot understand each other. It's like two people having a conversation but speaking different languages. No one said in the beginning, hey, the language we're going to speak is Spanish. The language we're going to speak is English. So that communication just does not work out. So they have to establish some rules before they start communicating. The message doesn't make any sense when the words are in the wrong order, right? That's another establishment of a rule. So in the first instance, you see, we have the same message here, but in the first instance, the words are not in the correct order, so you can't understand it. Computers have to deal with that too. So for the networks, when we put all these rules together, we have identifying a sender and a receiver, which seems like the most basic part. Having a common language, a common grammar, speed and timing of a delivery, and then confirmation and acknowledgement that that message has been sent or received. The source and the destination agree on the language that they're going to speak before they have their conversation. Then that gets communicated in English, and that's part of the message encoding. On a data network, encoding between hosts has to be in the right format for the medium that it's being transmitted over. So messages that get sent across the network are first converted into bits by the person that's sending it. So we know computers talk in ones and zeros, they talk in bits. So that has to be sent over the medium in bits. Each bit is encoded into a pattern of sounds, light waves, electrical impulses. It depends on the medium it's traveling on, right? If it's traveling on a copper cable, like the RJ45, the Ethernet cable that we're used to seeing a lot, it's coded into an electrical impulse. If it's going over fiber optic, it's converted into a wave of light. However that medium, whatever the protocol is for that. The destination down here is going to get it, and it's going to decode those signals in order and figure out what the message was supposed to be. So this message formatting and encapsulation that we're talking about, writing a letter with a message, you encapsulated it in an envelope so it can be delivered. Encapsulating ensures that just not anybody can read the message, right? They have to open the envelope to be able to see it. Then we address it, and we send it on its way. So there's a little bit about that, which we've kind of talked about. So that is our protocol for writing a letter. Here's all the different things that we have within it. If you look at the actual letter, you have who's going to get it, a salutation or a greeting, dear so-and-so. You have the message inside of it, and then a sincerely or a love or whatever your closing phrase is. And then you identify who you are that sent the letter. So that protocol has not changed in a really, really long time, right? That's a very tried and true protocol that we still use. Here we have a message, but we've put addressing information on it. So just like we have to address the letter, if we're going to send data over a network, it has to be addressed in a standard way so that the receiver can understand what we're trying to do. So we might put the physical hardware address or the source hardware address. So we talked a little bit about the OSI, the TCP/IP model, layer 2. Layer 2 talks in frames. So that is our layer 2 addressing. Then we have the start flag, which indicates, hey, this pattern of bits means that the message is about to start, so pay attention. Then we've got the recipient destination, the source, and then the actual bits, and then the ones that say, hey, this means that this message has ended. And in between that, we kind of have the formatting that we need to be able to identify this is a message being traveled over the network. So we normally communicate in sentences, right? Not run-on sentences, not paragraphs, not pages of information, but we tend to make a thought and then punctuate it so that the person that's listening understands that we're done with that thought, right? And if we're having a communication back and forth, you can tell when someone's done with their thought, normally because they pause or they stop talking, right? On data networks, message size comes into play when we talk about that. In computers, the source host is going to break up a really long message into little bitty pieces, almost like it's breaking it up into sentences. So it's going to have minimum and maximum size requirements. So a message can't be any bigger than this amount, otherwise it won't be able to be processed by all the devices on the network. Each frame is going to have its own addressing information, and then on the receiving end, they're going to reconstruct all those frames back together to make the message that was meant to be sent. We also have to deal with message timing. So in this instance, it's dealing with two different people that are both asking a question. But if two people talk at the same time, you can't understand what either one of them said. The same thing happens in data networks. So if every computer sends a message at the same time, you have to have a way of distinguishing who was talking to who so that everything can be interpreted. So there's some rules of engagement when it comes to message timing. The first one is access method. So that determines when somebody is able to send a message. If two people talk at the same time, what we have is a collision, right? Same thing on a network. Two packets collide, and neither one gets where it was supposed to get because they happen at the exact same time. So it's necessary for the two packets to back off and then try again. Just like if two people talked at the same time, they would say, okay, no, you go ahead. You retransmit, right? And then I'll say what I was going to say. The other part of that is flow control. So timing affects how much information can be sent and the speed in which that information can be delivered. So if one person speaks really, really, really quickly, it's difficult for the other person to hear because it's happening so fast they can't process it. So that's flow control. And a response timeout. If a person asks a question and they don't hear the response within an acceptable amount of time, they're going to say, did you hear me? Did you understand me? And that's a way of saying, I'm assuming that you didn't get that information because you didn't answer back. So in effect, that's kind of like a timeout. I'm going to wait an amount of time that I think is appropriate, and then I'm going to ask again. When we speak, we can deliver messages in different ways, in the same way that computer networks can. There's 3 different ways to deliver messages in an IP network. One of them is unicast. So unicast means from a source to one receiver, right? Uni means one. So it's a one-to-one conversation. So just two people talking back and forth is a unicast message. A multicast is a source to many people. So let's say out of half of you in this room, I talk and only half of you hear me for whatever reason. That is a multicast message. It's to multiple sources. There's also a broadcast. So that's the source to all receivers. That's me all talking to you right now. So I'm broadcasting out and you're all receiving my message. Same thing if you got on the intercom here and made an announcement. Everybody within range of that intercom would be able to hear you. That's a broadcast message. Computers work in the exact same way. On a network, you can send a unicast message from a source to one host. You can send a multicast from the source to multiple hosts, or a broadcast to everyone within hearing range. When it comes to IP networks, everyone within range is generally everyone that's connected with something, with a wire or with wireless. So that is the way that works as well. Any questions on any of that? Yes?
So you said on the intercom, that's like a broadcast?
That's a
And
broadcast.
then what you're doing right now is a multicast?
This is, well, you could call it a multicast too, yeah.
So
I
it's a
can see that.
broadcast.
I'm broadcasting to everyone that can hear me right now because the doors are shut, all right?
Yes, ma'am.
So that, yeah, you could call it that, or you could say I'm multicasting just to this room as opposed to the whole school,
Mhm.
okay? So let's talk about some protocols and standards. Who on earth sets all these things up? So there's a group of interrelated protocols that are necessary to perform communication. We call that a protocol suite. We touched on this a little bit last week. So in this instance, we're saying, okay, here's content. That's the question, where's the cafe? Then there's protocols, which is making sure that we use the same language so that we can communicate with each other. We're waiting our turn so that we're not talking at the same time. And we're signaling when we're finished by saying, where's the cafe? And then waiting for a response, right? So those are the rules that are established within that conversation. The physical layer, for example, is two people who are having this conversation. So protocols are about how the message gets formatted, how the message is structured, how these networking devices are going to share. They're all interconnected with wires or wireless, how they're all going to share and take turns to make sure that all this information gets conveyed. If there's an error message or there's some sort of system message, how is that going to get relayed? And then once we have a conversation and we're done having the conversation, what do? If two people are talking, they get done with the conversation, what happens? One of them probably leaves, or maybe they separate and they go to different sides of the room or something. So that's like a termination of a session. And that's another thing that a network protocol does. So here's an example of an interaction between protocols. So here we have a client that's going through the cloud, which is the internet, right? Whenever we see the cloud, think the internet. They're sending a message up to a web server. So they're probably requesting a web page, because web pages sit on web servers until we go access them, and then we can see a copy of it. So here we have the TCP/IP, the protocol stack with our different layers. So within that, there's lots of different things that are happening here that contribute to that stack. It starts at the network access layer, and it's accessing it through an Ethernet cable. So that's the bottom layer of the stack. The internet layer is the internet protocol, which is the IP addressing that's used to say, hey, this is where this is located, this is the sender, this is the receiver. That's another part of the stack. The transport is the transmission control protocol. We'll talk more about that in a second. The application is the function that says this is a web page. A web page is HTTP. So application says this is what HTTP looks like, and this is the way it's supposed to be used. So if I pull up a web page over here on my mobile phone, it looks like a web page, and it all has the same content in it. So these protocols work together in that way. So protocol suite is a set of protocols, we said, that work together to provide comprehensive network communication services. So all these protocols and all these different layers are formulated in such a way that anything will work with anything else to give us network services. So used to, we had things like Apple Talk, Novell networking. Those things are not available anymore. All HTTP is the same. All DNS is the same. All DHCP is the same, because it's formulated in that way. All these devices can interwork together. Different brands of different companies can work together. So IP is the same on a Dell switch as it is on a Netgear switch. It doesn't make any difference. It's a protocol. It's a predefined set of rules. So that's the reason why we can mix up different kinds of equipment in a network, and it doesn't make any difference, because those brands don't change what IP is. Okay? if you only had to buy Dell, Cisco, or HP branded equipment because they all work together in the same way, it would really limit you as far as what you could do on the network. And heaven forbid one of those companies goes out of business, right? Because then you can't get equipment for your network anymore. All these things are working together to provide that. So let's talk about the development of TCP/IP. There's an interactive timeline on Cisco Network Academy that will show you a little bit of this. In the very beginning, we had ARPANET. So this was a packet switching network. It's the grandfather of what we know to be the internet today. It was intended to only be used by universities and the government, because why would anybody else need the internet? As it turns out, we use it quite a bit. So there's a nice timeline of how ARPANET turned into what we use today. So this is the TCP/IP protocol suite. It's divided into 4 layers. There's different protocols used at each layer. You need to have a fairly good idea of which protocols are used at each layer for the purposes of this class and beyond. Going through Cisco Academy will help you define that a little bit better. These are some of the organizations that have come up with these different kinds of standards. Different organizations are concerned with different standards. If you go to Walmart and you buy a router, a little cheap router, you plug it in your network, you can use that router whether you have Apple computers, whether you have PCs, right? So whether you have a Dell computer or an HP computer, you can use that same piece of equipment because these people have established what a standard is. For example, next week, by the way, you'll need your toolkits when you come to class when we start going over chapter 4, because we're going to start doing some wiring exercises. So one of the standards associated with wiring is the TIA. They have established the color codes that go in a jack that plugs into the wall. They're always the same. That's a standard. And if everybody does the standard, then it always works. And if anybody comes into a network that they didn't build, they can look at that and go, that's the standard coloring. Now I understand what's going on in the network. So these are the people that have come up with some of these standards. They're all kind of concentrated on different things. These particular groups are responsible for standards on the internet, like researching and developing new internet technologies. There's all kinds of different groups around that. You don't need to know specifically what they do, but you need to be able to look at an acronym and understand that they're in charge of which part, right? They're in charge of the internet, they're in charge of cabling standards, electronic standards. These two are kind of important because they're specific to web traffic. So these are kind of the things where we take advantage of the fact that somebody's taking care of all the internet stuff and it all works, so we don't really bother with it. These are the people that are taking care of it. So ICANN and IANA keep track of who owns what domains and how to get there. So tstc.edu has an IP address. If you go to a browser and pull up tstc.edu, you're actually calling up the web server that holds the web page that hosts tstc.edu. They're the people that make sure that takes you to the right place. So they're kind of important on the internet. You do need to know them. They're keeping track of where that stuff is located, the different domain names, making sure there's not more than one tstc.edu, right? It needs to always go to the same place. It needs to be what you expect. And any port numbers involved with that, they're also checking out things like that. IEEE, Institute of Electrical and Electronics Engineers, one of the things that they really focus on is Ethernet and wireless technologies. And as you go, especially through Net Plus, and you start studying a little bit more on wireless, you're going to see a lot of these things. 802.1 and 802.11 you'll use. So 802.11 is the standard for wireless networks. So if we have a wireless network, how far does it go? How fast does it go? What are its limitations? They're the people that come up with that. So if you have an 802.11n network in different buildings, you would expect it to perform in the exact same way because it's a standard type of network. So there's some of the standards that you'll talk about. 802.3 we'll also talk about. That's the Ethernet standard. EIA, again, is the company, the TIA. They're best known for their standards in electrical wiring, connectors, the racks that hold computer equipment. If you've ever seen those, we've got them in several classrooms here. The coloring, the arrangement of those cables, they established that standard many years ago. There are two main models when we talk about network layering. So we've already talked a little bit about the TCP/IP model. By the way, you need to know these two models, you need to know every layer, and you need to know what they're for. I'll tell you why. This will show up in like every class you have here. This is a recurring networking standard. It is like chapter 1 or 2 of every textbook here, and it will be drilled into your mind. Depending on what class you're taking, there might be different models. They might focus on one more than the other. In Network Plus, we focus on the OSI model. When you're talking about Cisco, they focus on TCP/IP. When you get into security level stuff, they'll talk about the Department of Defense model. But what you really need to understand about these is they're segmenting off different parts of networking so that different devices can be interchangeable. A layer 2 switch is always a layer 2 switch, and it doesn't matter where you get it or what it looks like or what brand it is. You should be able to plug it in and expect it to do layer 2 switch things. The difference between these two models, the OSI, they really spaced it out, and then the TCP/IP, they said, we're going to group some really similar things together because it makes sense to us. That's about the difference there. As far as the different layers and what they do, the physical layer is cables and hubs. Those are the devices that we would see on the physical layer. Those are things that are actually transmitting bits, ones and zeros, on a wire. That is a physical layer thing. The data link is the next one up. You're sending data inside the local area network. That is bridges and switches. They're layer 2 devices. Layer 3 is the network layer. That's sending something outside of your local network, like to the internet. If you're going outside of your local LAN segment, you need a networking device to be able to do that. So when you see a router in a topology, that means it's going to the outside. If you don't see a router, that means it's just within that one little segment of devices. The transport layer segments and reassembles data, so it breaks it up in chunks and then puts it all back together. The session, set up, maintain, and tear down sessions. It's always the easiest to remember because it always has the word session in it. So if you're doing some kind of drag and drop, you get that one every time. The presentation is the way that data is presented. For example, encryption is part of that. So if data is going to be encrypted, it happens at that layer. And we know that encrypted data looks different because it's all scrambled up. It's presented in a different way. And then the application layer, the way the data is presented to the application. HTTP is an application layer protocol. It's the thing that says this is what this web page looks like no matter where you go look at that web page. That's what HTTP does for us. You do need to know all these. There are acronyms, if that's helpful, to help remember this. Starting from top to bottom, all people seem to need data processing is one that people use. Bottom to top, please do not throw sausage pizza away. That's one people use. We had another instructor up here that came up with please do not touch Superman's private area. I tend to like that. There's one about Ninja Turtles that I can't remember. But coming up with an acronym to help you remember those will get you far on that. There's also...
Please don't go away Superman's private area.
Yeah, I'll remember not to touch Superman's private area. We have what we call protocol data units at every layer. So each layer we talked about, this talks about bits, this goes within. There's also a unit of measure for each one of these layers. So, and I have an acronym for that too, because of course I do. So, and the physical, everything is in bits, right? The data link, everything is in frames. Network, everything is in packets. So you would say something like an IP packet. IP is a network layer protocol, and it's measured in packets, okay? Bits, frames, packets. Transport is in segments. You can kind of see some of these from the description here. And then everything else we can call data or payload for those 3 layers. The way I always remember this was by first person shooters, please. That always helped me remember it. I'm sure I have some players in here. So you do need to be able to recognize those. I just flipped over to another slide, so don't get confused. We can go over that again if we need to. But those are the different protocol data units for the layers in the OSI model. And again, we have the TCP/IP model, so it's the same kind of thing. They just squish some layers together, but essentially they may have called the internet layer instead of the network layer, but it still does the exact same thing. So it just depends on how that data is being presented to you. So again, you need to know those layers, the order they appear in, and what they do. If a message is really large, like a really, really long document, it's going to take more than one packet to transmit that data. So if the message would get segmented, it would get taken apart, put in chunks. Like if you got multiple boxes from UPS and they were labeled 1 of 4, 2 of 4, 3 of 4, 4 of 4. So those boxes have been segmented because maybe what's in the boxes is too big to fit in one, or maybe it's too heavy to fit in one. So that's what message segmentation is on a network. Breaking those messages up into smaller, more digestible pieces. Because you have to think, if you send a really, really long packet through a router, the router probably wouldn't be able to process it because it's got to process that instead of all the other things that are happening in the network, and then something might get dropped, right? It may not work out. That's what message segmentation is. Multiplexing is something that's used, so if somebody sends a big file, they don't hog the whole internet connection. Parts of their file get sent, other files can get put in the queue, and between the two of them, they all end up where they're supposed to get. Breaking the things up in chunks helps with that. So again, segmenting lets us have different conversations at the same time. It increases efficiency and it adds a little bit of complexity to our network. When we get to security issues, we'll talk a little bit more about why that's important. The protocol data units, as we spoke about, that's how we measure the data at each level. And here's a little bit about that by first-person shooters, if you can remember that. Bits, frames, packets, segments. And then everything else can be called data or payload. As a packet goes from the web server to the web client or back and forth, encapsulation occurs. So as it moves up and down the different layers of the OSI model, that process is called encapsulation. And then we're going to watch a little bit of a video about that. So from the initial sender to the receiver, it goes up or goes down the OSI model and things get added to it. When the receiver gets it, they start stripping off pieces of it till they get back to the data. We're going to watch a video about how that occurs.
I love the comedian Steve Martin. The guy is an absolute genius. One of my favorite quotes that he makes is, talking about art is like dancing about architecture. And for those who are into the art scene, it makes total sense because sometimes you just have to appreciate the art by enjoying it and encountering it. And to me, that really is kind of like the OSI and TCP IP models as well. The challenge with these models is, oh, we can draw the pretty boxes up and discuss each level's function, but until you actually watch it happen, it doesn't really make sense for you. So that's what this episode is all about. I'm actually going to be putting on different hats, and I'm going through interpretive dance, going to show you all of the different layers of the OSI and TCP IP models, and we're going to be doing this working with an Ethernet frame. Now, in this scenario, what's going to be happening is I'm going to first start off as a client system, and I'm going to be just sending out a HTTP request to open up a web page. And then on the return, I'll be acting like a web server who's actually bringing all this information back. And we're going to see how every step in these models works together to make all this happen. So let's go ahead and start all this. I'll be right back with a hat. Hi, I'm the lowest layer of both the OSI and the TCP IP model. Now, there's a lot of different layer pieces involved here. So for right now, pretend like I'm a network card. And I'm just sitting around and I'm waiting for some data. Oh, here comes a frame now. So here is an Ethernet frame. Now, with this Ethernet frame, my job as a network card is really to, first of all, take a look at the incoming MAC address and verify that it's for me. In this case, it is, so I can take this data. Now, the first thing I'm going to do is I'm going to take a look at the frame check sequence. I'm going to check the entire Ethernet frame to make sure that it's in good shape. And assuming that it is, as a network card, I can go ahead and strip this off, and I can strip off the MAC addresses. Now, if I'm a good network card, and aren't we all these days, I'll keep this information, and I'll store this off to the side somewhere in memory, primarily because I want the MAC address where this came from, because later we might want to be sending a frame back out. So what I have at this point is an IP packet. Now, my job as a network card is pretty much over at this point. So let's consider what we've just done. If we're taking a look at the OSI model, we've basically covered layer 1 and layer 2. So we've got the physical layer and the data link. The physical layer is going to be really more of the actual connection I have to the outside world, the cabling and the hubs and all that type of stuff. And then the layer 2, or the data link, is when I'm looking at the MAC addresses. Now, on the TCP/IP model, they make it pretty easy. They just call all of this stuff that I've just done the link layer. So with the link layer, that handles both of the OSI's physical and data link. Oh, and by the way, not only do you call this the link layer sometimes, you also call it the network interface layer. So my job here is done. So what I need to do now is pass this IP packet up to the next layer. Thank you, lower layers. Hi, I'm what you call in the OSI model the network layer, or if you're the TCP/IP model, it would be called the internet layer. My job is real simple. I have to deal with IP addresses, and that's pretty much all that I do. When I'm looking at these IP addresses, my big first number one job is to make sure that this IP address is for me. And in this case it is, so I'm happy. So what I'm going to do is I'm actually going to pull this IP information off. And now that I've got this IP information, I'm going to get rid of this one because I know my own IP address, but I'm going to keep the IP address that it came from. Just as the lower layers will keep MAC address that they come from, I'm going to keep this for myself because I'm probably going to want to send an IP packet back in a little bit. So this is, I've got an easy job compared to a lot of the other layers. And what I'm left with is, well, it depends on what type of packet, but in this case, I'm left with what's known as a TCP segment. This TCP segment is designed and it's ready for my computer. The challenge now is to get it to the right applications and in the right format that those applications can use that. Luckily for me, that's not my job. All I have to do at this point is pass it up to the next highest layer. Thank you, lower layers. Okay, hi, I'm the transport layer, and I'm actually kind of cool because I'm exactly the same on both the OSI and the TCP/IP model. My job as the transport layer is to act as the assembler, disassembler of data. Now, keep in mind that what I'm holding right here is probably, well, it depends. It could be all the data. If this was just a simple HTTP request, this might be all the data in one little piece. But it could be other things. For example, what if I have a big web page that's coming in? And what if I've got a big Word document that I'm copying? Or what if I've got big chunks of data? Well, that's what I'm all about. My job is to take data, and if it's big and going out, I'm supposed to chop it up into little bite-sized chunks. Equally, if a bunch of data is coming in, my job is to reassemble all this data. And I'm going to do that using the sequencing number. The sequencing number is kind of like, if you ever gone to UPS and you got a whole bunch of boxes, and it'll say 1 out of 20, 2 out of 20, 3 out of 20. Well, that's kind of like how sequencing numbers work as well. So either I'm disassembling and adding sequencing numbers to individual TCP/IP segments, or I'm getting a bunch of TCP/IP segments in, and I'm going ahead and I'm reassembling them using the sequencing number. The bottom line is that at the transport layer, things get a little bit strange. Now, I'm going to keep my data, but not only am I going to keep my data, I'm going to take the sequencing number off. Now, keep in mind, at this point, this data is complete. Whatever it is, it's a complete chunk O data. The only thing left are my port numbers. Now, these port numbers, they don't really get reassembled, but I'm going to kind of pretend like they do, because the next layers above me are going to need this. So, my job at the transport layer is done, and I pass it up to the next layer. Thank you, lower layers. Hi, I'm the very top of both the OSI and the TCP/IP model. Now, on the TCP/IP model, I'm just called the application layer. But on the OSI, I'm called session, presentation, and application layer. So, since TCP/IP makes it a little bit too easy, let's concentrate on the OSI side. The session layer is really designed to connect a server to a client on a remote system. Now, on today's systems, we have applications that are network aware. We have web pages and email and FTP and World of Tanks and all these things. So on the TCP/IP model, making a session doesn't really make sense. It's the applications, the moment you fire them up, they are by definition going to try to connect to something. I mean, try to fire up an email client and not connect to your email server. Get the idea? Now, back in the OSI days, you would have operating systems that were not network aware. You'd have something like Microsoft Word, and it couldn't save to anything but a drive letter. So we used to have a distinct session layer that allowed us to connect to a remote system as opposed to, say, just saving to our hard drive. Now, the next one is probably, in fact, this should be erased in my opinion, and that's the presentation layer. The presentation layer was designed a bazillion years ago because we would get the data to a particular application, but it wasn't in a form that the application itself could use. So you would have text files that were stored in weird things. You may have heard of ASCII files. Well, there was a time when they had names like EBCDIC and crazy stuff like that. So the presentation layer has kind of pretty much disappeared. So that leaves us with the application layer itself. Now, when we're talking about the application layer, we're not talking about the actual applications. We're not talking about your actual web browser. We're not talking about your email client. We're not talking about your World of Tanks client. What we're talking about is the built-in smarts that allows them to interface to a network. So my job at this layer is really more than anything else. Within TCP/IP, I'm taking a look at my port numbers. And my job at this point is to take a look at the port number, and I see that this is port 80. So I know that this needs to go to my web server. So what I'm going to be doing is I'm going to be taking this information off, and you'll notice that I have the return port number. And again, I'm going to keep this, I'm going to put it in memory someplace in case we need to send that back later. So my job is pretty much complete. I know it's port 80, and I know to send this up to the right application and let that application do the voodoo and do so well. Okay, now that was fun, but what I want to do now is actually reverse the process. What we just did is we took an incoming Ethernet frame and turned it into data that our applications can use. So what I want to do this time is start with some data, and we're going to send out an Ethernet frame. So let me start back up at the top, and what I'm going to be doing is I'm going to be receiving data from an individual application. Now, my job here is to make sure that this data gets to the right computer over there. So the first thing I'm going to be doing is I'm going to be taking the information, and this is the port numbers that I got from the incoming frames, and what I'm going to do is reverse them. So now the destination port number is going to be 1423 because that's where it came in from, and the source port number is going to be port 80. Now I'm not even going to put them together at this point. Basically what I'm saying is this is the connection, and I'm going to send it down to lower layers. So I guess I need another hat. Okay. So So now I'm the next lower layer. So what I'm going to be doing here is the transport layer is I'm going to be taking a look at this data. Now, if this is a lot of data, and if I'm a web server, this is probably a great big web page. So I'm going to have to bring in some sequencing numbers. I need some really bad magician music right now. Here we go. All right, so I'm going to start breaking all the data up into individual chunks that are big enough for individual IP packets. And I'm going to be making, in this case, a very pretty TCP segment. So once the TCP segment's done, now I have to go down to the next layer. And, okay, here we go. All right, so now I'm the network or the internet layer. And what I'm going to be doing is I'm going to be taking the IP information that I had got from the original incoming data. And again, since I'm sending it back to the guy who sent it to me, I'm just going to reverse these. And I'm going to plug that in. And now I've got my IP packet, which is ready for the next layer, which is going to be, hate a hat backwards. Okay, so which is the next layer, which is going to be the physical layer, or the data link layer, or the network interface layer for the TCP/IP model. And in this case, what I'm going to be doing is, first of all, I'm going to be putting on the MAC addresses because I'm in Ethernet now. And, whoop, I'm not quite done because I have to go ahead and run another frame check sequence. And get this guy in, and ta-da! I have now completed the process in reverse, and I send it out very carefully, and the job is done.
Okay, so there is an illustration of how what he was demonstrating was encapsulation and de-encapsulation, sending a message back and forth across a network. Let's talk a little bit about network addressing. All of these components deal with delivery, but I do want to stress that the data link is on the internal network and the network is on something external to that network. But different kinds of addressing occurs at different layers. So the physical, again, we're worried about timing. We're worried about bits being synchronized, so they're occurring in the right way. The data link, we're worried about the physical address, which is the MAC address, which for our layer 2 devices, physical MAC addresses. With the network layer, we're worried about logical addresses, which is our IP. Logical addresses can change. Physical addresses are set in stone. Okay. With transport, we're worried about port numbers, which are the little blocks that he was talking about there. And then in the upper layers, we're worried about just the data that we're trying to send. So we have to have all these things in play, and they all have to be just right for data to make it to where it's supposed to go. So routers are to get to an outside network. So in this case, this packet is going across 2 routers to get to a web server to reach its destination. So since it's hitting a router, we know that we're expecting an IP packet, okay? Because IP is a layer 3 protocol. A packet is what we measure things at layer 3 with. And if it's going over a router is what's going to connect us to another network. The sooner you understand how that works, the easier this class will be, because that tends to be a recurring theme. What's internal, what's external to the network, and what devices are used at each one. So in this instance, we're going across multiple networks from the original source to the destination, which is a web server with a packet. So our data, we've got different kinds of addresses. We've got the network address. So we have a source where it's coming from. We have a destination where it's going. So the network address is responsible for delivering that. The data link address, again, we have a source, we have a destination, and that's responsible for delivering on the same network. Even if we move, because we use the encapsulation process that we just saw in the video with the guy with the different hats, even if we move across to another network, that layer 2 information is still there. It just gets covered up by the layer 3 information. So it's not used once it hits outside the network, but it does still stay there as that packet moves across. So here we have, even though we are moving towards the web server, we still have that original information that has to do with those physical addresses. It's just all wrapped up in those packets. The same applies for devices on the same network. We might still see network information, but that address is on the same network. It's not going to have to pass over a router. We still use an IP address, but it might not actually get noticed because it might not be needed. You'll see that more. We've got a packet tracer exercise that shows you how those things step through, and that will make more sense when you do that. There's different portions of the network layer address. There's a network portion. That's the part on the left that tells you the network where that IP address belongs. We're going to go into like exhaustive detail about this in different chapters. There's also the host portion that specifies the device. That will make more sense later on. Again, we have the source, the destination IP address, and the source and destination MAC addresses. So you're going to see lots of different kinds of addresses when you actually start looking at packets moving across a network. Again, we have devices on our remote network. They've kind of simplified the addresses, but you would see data link and network side by side. That's a little more of the same.